Let's do solutions for assignment 4.1 and some practice with related rates. So if possible, if there's a diagram here in this problem, a sphere, there's not too much that's interesting because the formula just depends on the radius of the sphere. But we know that we are given the rate at which the volume of the sphere is changing. So here we are given dv dt, the change in volume with respect to time. And we are looking for how fast is the radius increasing. So we are looking for a change in radius. So we want to find a dr dt. So thinking about what rates are given and what rate you're looking for helps you to know what kind of formula you need. So we are looking for a formula that involves volume and radius of a sphere. So we have a static model from geometry that will work for the volume of a sphere, 4/3 pi r cubed. And when we differentiate with respect to time, we will come up with our related rates model. And it will show how dv dt is related to dr dt. So I'm going to do a ddt, differentiate each side with respect to time. So I get a dv dt on the left side. And the 4/3 pi can come out in front, but if you're thinking one step ahead for your power rule, we're going to reduce the power. So when we bring this 3 down, it'll cancel with the denominator. So we'll have 4 pi r squared. And don't forget the chain rule, dr dt. So there's our related rates model. And then the next thing that we need to do is think about our specific case. So we want to substitute the specific case here. And in this case, all we need is when the diameter is 30. Well, don't be fooled by that. Diameter doesn't appear in our formula. So make sure you adjust that. We want to substitute 15 for the radius. So let's see what we were given here. We were given dv dt. So let's put in 100. And you might not always write the units, but let's do that for this first case here. 100 cubic centimeters per second. And on the right side, we want to substitute for r, our specific case of 15 centimeters. And then don't forget to square it. And the only variable left is what we're looking for. We want to solve for dr dt. This was what we were asked to find. So on the right-hand side, 15 squared is 225 square centimeters. 4 times 225 is 900. So think what's going to happen here. 100 cubic centimeters per second divided by 900 pi square centimeters. And again, you're not going to show these units each time, but to make it very clear that the square centimeters cancels into the cubic centimeters. So you can leave your answer in exact form. 1/9 pi centimeters per second is the change in radius with respect to time. If you wanted a more meaningful, if you found it more meaningful, you could convert that to a decimal value. Make sure you give at least 3 decimal places of accuracy. All right, let's try another practice problem here with a ladder. A ladder, I think I dropped something there. A ladder 10 feet long is resting against the building. So our hypotenuse in this case is our fixed length of the ladder. It's not a variable. The ladder is going to slide down. So here, if the bottom of the ladder slides away, so we are given the rate that the horizontal side is changing in the positive direction here. So we are given that dx dt is 1 foot per second. And the top of the ladder is going to come sliding down. So let's use y as the vertical height. So we want to find the change. So we want to find the dy dt. So again, if you think about what rate is given, dx dt, and what are we looking for, dy dt, that tells you what we need to do as a static model is come up with a relationship between x and y. And of course, this is Pythagorean theorem, so x squared plus y squared equals 10 squared, or 100. And then our related rates model comes from differentiating implicitly with respect to time. So I'm going to differentiate with respect to time. So I'm going to do a d dt operator. So the derivative of x squared is 2x with a chain rule on the x, dx dt, plus the derivative of y squared, 2y, with a chain rule on the y. And on the right side, the derivative of a constant is 0. These 2's, you can leave them there, but we could divide an equation by a constant. So we could divide 0 divided by 2 is still 0. Gives us a little simpler formula. And now we want to plug in our specific case. And when you have a geometric relationship, stop for a minute and analyze your specific case. For our sphere a minute ago, it was just the radius. But here we might want to think a little bit more. The specific case we're interested in is how fast is the top of the ladder moving when the bottom of the ladder is 6 feet from the wall. So let's redraw our triangle. Okay, I paused the video and lost a little of my writing here. So the specific case is worth redrawing here. So we are looking for the triangle where the ladder, of course, is always 10 feet. The distance from the wall for our specific case is given to be 6 feet. So they don't tell us all 3 sides of the triangle, but of course, by Pythagorean theorem, and here, because it's a Pythagorean triple, we know what we're going to substitute for the y value, even though they only gave us the x value. So now our specific data, our specific case gets substituted into our related rates model. So x is 6 feet. dx dt was 1 foot per second. And I lost again. I didn't realize how my tablet. Let me put this back the way it was, and then I had canceled out the 2's. All right. So now we're back up to date. So x is 6. dx dt is 1 foot per second. Y is 8 feet, the vertical height. dy dt is the variable we're looking for. So it is the only variable left. So here we have 6 square feet per second. We can move that to the other side. And it will be negative 6 square feet per second. And then we're going to divide both sides by the 8 feet. So negative 6 over 8, or negative 3/4. And square feet per second divided by feet to the first power will give us the correct units we were looking for of negative 3/4 feet per second. The negative, of course, tells us that the top of the ladder is sliding down at that point. All right, one more. Okay, here we have, making a good diagram is going to be essential here. So ship A starts out 150 kilometers west of ship B. So at the starting point only, this distance happens to be 100. So at noon, this distance is 150 kilometers, but it's not going to stay that way. Ship A is sailing east, so ship A is headed this way. So at every point in time, it's going to be at a different location. And likewise, ship B starts at this position, but it is actually sailing north. So ship B is going to keep moving. So these are A0 and B0, and they're going to be in different positions. So what else do we know here? We know that ship A is moving at 35 kilometers per hour. Well, let's use X again for the horizontal axis, Y for the vertical. and a Z for our distance between the two ships as they're moving. So the two ships could be at all different positions. So for example, at some point in time, this will be our hypotenuse Z. At another point in time, this might be our hypotenuse Z. So we're just drawing one representative right triangle. So the distance between the two ships, wherever they are, at some time A might be here and B might be here. So Z represents the hypotenuse of our right triangle in any case. All right, so what do we know about the rates? We are given how fast ship A is moving in this direction. So that is our dx dt rate. And it is moving at 35 kilometers per hour to the east. And we are also given how fast ship B is moving. Ship B is moving north, so let's call that the dy dt. And it's moving in the positive direction, 25 kilometers per hour. And dz dt, how fast is the distance between the ships changing? So we are looking to find a dz dt. And our specific case is at 4 o'clock, but don't worry about the specific case yet. First, we need to come up with a general model. So notice that our rates has an x, a y, and a z. So your static model has to simply be a geometric equation that involves those. And of course, again, I don't think this will cause trouble for anyone when it's a right triangle. Use Pythagorean theorem. We're interested in the three sides of the triangle. And then our related rates. And you might already get the idea here that they're each going to have a 2 in front. So you might say, should I just cancel the 2's right away and not even write them? And that would be fine. But in case someone doesn't quite realize what I'm saying there, let's put the entire derivative, and then you could divide this equation by 2, since every term can be divided by 2. All right, now we want to plug into our related rates model. We have 6 different variables, but that's okay. We're going to be able to substitute 5 different numbers, and the only thing we're looking for is dz dt, so that's going to be the only variable left. So let me get some space here and let's make a diagram of our specific case. Don't try to do this in your original diagram. I think you have too much information. So remember that the ships have been traveling for 4 hours. So ship B started down here and it moved up here. So at noon it started and it traveled for 4 hours. And remember that we knew its rate was 25 kilometers per hour. So the specific case here is at 4 o'clock p.m. They've been traveling for 4 hours. Now remember that ship A started at 150 kilometers. So ship A started over here, but it's been traveling for 4 hours at a rate of 35 kilometers per hour. So in 4 hours, 2 times 35 is 70. So 4 times 35 is 140. So ship A has traveled way over to this position by 4 o'clock. So let me erase where it used to be. And now we know that this distance is only 10 kilometers. Now we've got a bit of a problem here if you look at the difference between the way our ladder diagram was drawn a minute ago. Think of your XY axis. I think that you would agree that this is a coordinate of negative 10 units on our axis, because eventually ship A is going to end up over here. Eventually, when ship A crosses the origin and ends up over here, then we'll have to have a way of specifying that it is now in a different part of the coordinate graph. So we might say that this position right now is at negative 10 kilometers. And then do we know the distance between them? Well, think of Pythagorean theorem. And of course, you could make this simpler here if you factor out the 10. Factor out the 10 so that you just do negative 1 squared is positive 1. 10 squared is 100, so 1 plus 100, 1. 1 plus 100 is 101. So there's our z value, 10 square root of 101. And that's now the specific case that we want to substitute. So let's see if I can do this so that you can follow. Our x coordinate is at negative 10. Our dx dt is the rate of that ship, 35 kilometers per hour. And let me just put the units in at the end here. And our y coordinate is 100. And our dy dt is that speed, which was 25 kilometers per hour. And on the right-hand side, we know what z is. We just found it, 10 radical 101. And we don't know what dz dt is. That's what we wanted to find. So on the left-hand side, we have a negative 350 and a positive 2500. So it looks like we've got 2150 divided by, we're going to bring this to the other side, 10 square root of 101. And that would be, if I don't forget to put on units, that would be in kilometers per hour. That would be the rate at which the ships are, the distance between the ships is changing. So if we round that, if you'd say, well, I'm not sure what exactly that means, you could grab your calculator, and I happen to have done that already. It is about 21.393 kilometers per hour. So if you do round, then change your equal sign to an approximate. So the exact answer is, of course, always acceptable. If it makes more sense to you to convert it to a decimal, so this answer is acceptable as well.